In the section that's about approximating rates of change in the textbook, the idea of a limiting value or limits is introduced. The idea of approaching, if you have a sequence of numbers and it's a pattern, do they approach a value or do they go off to infinity? And that idea of approaching and converging upon is huge in mathematics. It allows you to explain so many things. And as I mentioned previously, Archimedes was huge in developing that idea in 250 BC. He said, what if I had an n-gon, a regular n-gon with n sides? What if I made larger and larger numbers of sides to this thing, and the sides would get smaller, they'd approach zero, and eventually that n-gon would become a circle. And so you could study that convergence from a regular n-gon to a circle. And that idea is built into so many ideas in calculus, and many students in pre-calculus will go on to take calculus, because calculus is based on using limits to study these instantaneous rates of change, kind of like you're doing in this section. An average rate of change for a function can be defined between 2 points in the function. You create a secant line to go through those points, and you find the slope of that line, and that represents the average rate of change. But it's incredible, guys like Gottfried Leibniz, who did this theoretically, and Isaac Newton asked this question that really changed the world at the time. Around 1700, separately, both of them asked the question. They were studying, Leibniz studying theory in math, Newton studying the universe, and they said, well, could we look at something and not find the average rate of change between 2 points, but find out what's going on in terms of rate of change at one point? For example, Newton looked out across the universe and he studied planetary motion, as so many mathematicians and scientists did for thousands of years, because people wanted to describe the world around them. And he said, well, I can figure out how fast this planet is going between this point here and this point here, way over here, because I know it's an elliptical motion of the planet, and the path is elliptic, so I can just kind of figure out how long that path is, and go from there. But it was Newton who said, but that's not good enough. I want to look at that planet right now, right at this instant in time, and I want to know how fast is that planet moving right now, and other objects in the universe, since there's so much movement of objects in our universe. And that idea spawned the study of limits, because you have to converge from average to instantaneous, and the idea of finding limits and according to accumulation, which is also a rate of change. So you could do this as well in non-constant situations. Physicists and mathematicians usually said, well, we can approximate this with a line, we can model this situation with a line, or with a constant, a straight line, or some type of line with slope. But that's usually not a good enough approximation. Once you can hone in on what's happening instantaneously, you can deal with curves and non-constant situations. And really, that's what made engineering, and still does. I mean, our buildings wouldn't be here, the bridges we build wouldn't be here if it weren't for those that someone was bold enough to ask that question. And I'm going to remind you that one of the things you're teaching your students is to ask those kind of questions. Not just do the mathematics, but think deeply about it. And you should always say, do you have further questions? Because that's what leads to discovery.